Okay, let's unpack this. We pulled together some really fascinating sources today. They all map out these huge shifts in how we've tried to understand the cosmos. Our mission, really, is to dive deep into that journey. From thinking the universe was this eternal, fixed, absolute sort of box, to seeing it as dynamic, relational, even self-organizing, like modern physics tells us.
Yeah, it's not just one big leap, is it? It's more like a series of, well, conceptual earthquakes, one after another.
Yeah.
And it's striking how long those older fixed ideas really hung on. Even during the big breakthroughs, the Renaissance ones. The ultimate goal, of course, is still that unified theory. It's something that tells us what space and time are, what stuff is made of, how it all works together. We're not quite there yet.
Right. We tend to jump straight to Einstein, but maybe we should start earlier because
Yeah.
it's key to grasp how limited that first big shift actually was. We call it the Copernican revolution, but for Copernicus himself, or Kepler, even Galileo, how big did they really think the universe was?
Well, surprisingly small, actually, by today's standards. The sources really emphasize this. Even with the sun at the center, they still pictured the universe as uh, finite and spherical. Just big enough, really, to hold the orbits of the 6 planets they knew then, plus a little bit of extra room.
So when you looked up, you weren't seeing infinite depth,
Yeah.
like scattered stars forever. You were seeing a boundary.
Pretty much, yeah. A
Yep.
wall, the distant stars, they literally thought they were fixed like lights stuck onto the outermost sphere.
Yeah.
That was the edge of everything. Think of it less as, instantly opening up infinity and more like just rearranging the furniture inside a very large but definitely closed room.
That really puts it in perspective, the conceptual gap there. It took, what, over 150 years for Newton to come along with universal laws, infinite space, atoms.
Yeah, that jump from that finite sphere to Newton's infinite clockwork universe governed by laws, that was arguably much more radical than just swapping the Earth and Sun.
Absolutely monumental. And that long search for the complete picture, it leads us, doesn't it, straight into the challenges we face now. Today, the huge task is unifying quantum theory and general relativity. But chasing that, well, it throws up this really deep philosophical problem, the sheer, almost miraculous hospitality of the cosmos.
Exactly. When you step back, the very possibility of life, or even just complex chemistry,
Yeah.
it all hangs on one thing: stars.
Stars, right. The cosmic ovens.
That's it. They forge all the heavier elements, the carbon, the oxygen, everything we're made of,
Right.
basically. But the fact that stars exist at all seems to depend on certain numbers, certain parameters being tuned with just unbelievable precision.
Okay, let's take gravity first. The sources point out something that feels backwards. Gravity is incredibly weak. How is that weakness actually essential for making stars, especially ones that last billions of years?
It's this incredibly fine balance. If gravity were even, say, 10% stronger, the universe might have just collapsed back on itself almost instantly, or at least way too fast for anything complex to form. But its actual weakness is key, because it means you need a truly enormous amount of stuff. Huge clouds of hydrogen and helium to pile up. Only when you get that massive accumulation does the pressure in the core get high enough to kickstart nuclear fusion.
So, the reason stars are so huge and last so long is precisely because gravity is so feeble.
Exactly that. The weakness means you need a massive amount of material. If gravity were much stronger, stars would be tiny. They'd burn through their fuel incredibly fast. They might only last thousands of years, maybe millions, not the billions you need for planets to cool, for life to evolve.
And it's not just the big forces like gravity. What about down at the atomic level? The proton and neutron.
Ah, yes. That's
Yeah.
another knife-edge situation, really. It underpins all of matter as we know it. Stable chemistry, the kind life needs, depends on this tiny, tiny mass difference between the proton and the neutron. The neutron has to be just slightly heavier than the proton by about the mass of an electron. If that wasn't the case, well, stable nuclei just wouldn't form properly. No stable nuclei, no chemistry. No chemistry, no complexity. Gone.
And when cosmologists try to calculate just how finely balanced those early universe conditions had to be, just to allow stars and galaxies to form at all, that's where the numbers get truly mind-boggling.
Oh, completely. To get a universe that lasts long enough, billions of years, not just a fleeting instant like the Planck time, 1043 seconds, you need the initial expansion rate and the amount of matter to be balanced perfectly.
Let's try and make that number real for you listening. Measured in basic Planck units, the accuracy needed for those starting conditions is about 1 part in 1060. That's a 1 followed by 60 zeros. What does that kind of precision even look like?
Yeah, well, it almost defines analogy. Imagine trying to fire a rifle across the observable universe and hitting a single specific atom on the other side. Or Like the sources suggest, maybe covering North America in marbles,
Right.
right? And needing to pick out one specific marked marble to make the whole universe work. That's the kind of ridiculous accuracy we're talking about.
Which brings up this huge question that kind of hangs over everything in unification physics, doesn't it? Is
Yeah.
this incredible life friendliness just built into the math somehow, a necessary outcome? Or is it just a wildly improbable accident and we're just lucky enough to be here to see it?
And the sources show how much that challenges our basic assumptions.
Yeah.
To think that mathematical consistency alone could somehow force the universe into these incredibly specific, life-friendly parameters, it pushes you toward thinking maybe something else is going on, something maybe relational, not just pure chance.
That level of fine-tuning, it almost forces us to look beyond the numbers themselves and question the stage everything happens on, space and time. Which leads us into this long-running philosophical debate that's actually at the heart of modern physics.
Right, the clash between the absolute view and the relational view. The absolute view that's Newton most famously saw space and time as these rigid, fixed structures. They exist on their own, unchanging, like an empty container waiting for reality to happen inside it.
A totally fixed backdrop, immovable.
Correct. Then you have the relational view. You can trace it back to Leibniz, and later the physicist Ernst Mach really pushed it. They argued that space and time aren't things in themselves. They're just ways of describing the relationships between objects and events.
Right.
If you took everything out of the universe, all matter, all energy, then space and time themselves would just disappear because there'd be no relationships left to describe.
Okay, that sounds philosophically interesting, but how did that relational idea actually become part of science?
That's the crucial link. Mach and Einstein. Mach argued really strongly that when you feel acceleration, being pushed back in your seat, you're not accelerating relative to some imaginary absolute space. He said it must be relative to everything else in the universe, all the distant stars and galaxies. Inertia, he thought, was somehow caused by your relationship to all that faraway stuff.
And Einstein picked up on that. He didn't just think it was a neat idea, he built it into his physics.
He did. Einstein made it concrete with the equivalence principle. The idea that feeling acceleration and feeling gravity are basically the same thing, physically indistinguishable. By connecting inertia, the resistance to acceleration, to the distribution of mass and energy, which is gravity, well, general relativity showed the stage isn't fixed at all. It's dynamic. It bends, it stretches, it's woven together with the matter and energy within it. It's relational.
And this tension, this absolute versus relational idea, it doesn't just apply to space and time, does it? It applies to matter itself, the atomic conflict.
Absolutely. The old way of thinking about atoms, traditional atomism, saw fundamental particles as kind of eternal and independent entities. Their properties like mass, charge, were just fixed, inherent things, unchanging. That's the absolute view applied to matter.
So in that old picture, a neutron is a neutron is a neutron. Its properties are exactly the same, whether it's floating alone in space or part of, I don't know, your fingernail.
Seriously. But modern physics really struggles with that idea of rigid independence. There's this deep tension, especially in unification theories. How do you unify everything if the fundamental building blocks have these eternally fixed properties that are totally independent of the universe they exist in, independent of its history, its context? If the universe is truly relational, right down to the foundations, maybe even particle properties aren't absolute. Maybe they emerge from relationships with fields, with the whole system, not set in stone from outside.
Which leads us neatly into the final big conceptual shift we wanted to cover. The idea of the universe not as some fixed clockwork machine, but as a self-organizing system, something dynamic that evolves complexity over time.
Yes, this is a huge break from that old Platonic ideal or even the Newtonian view, and it counters that 19th century fear of the heat death of the universe, right? The idea that everything must eventually just decay into a uniform, disordered state, maximum entropy, a cold, simple, boring cosmos.
But we know life seems to defy that trend towards disorder, locally anyway, because Earth isn't a closed box, it's an open system. There's this constant massive flow of energy coming in from the sun.
And that's absolutely critical. If the universe were truly cold and dead, no stars pumping out energy, then planets like Earth couldn't sustain life. They'd eventually just reach thermal equilibrium with their surroundings. Game over. The stars are essential because they create these huge energy gradients. They keep pockets of the universe far from equilibrium, allowing complexity from quarks building atoms to cells building ecosystems to emerge and persist over billions of years.
So the universe isn't just capable of having complexity, it seems almost geared towards organizing itself on multiple levels. This relational thinking also seems key to understanding the forces themselves, right? Through the gauge principle. Can you unpack that idea, maybe Herman Weill's original thought, in simple terms?
Okay, the gauge principle is pretty radical because it's all about relationships. It starts with something like electric charge. Does it fundamentally matter which particle we call positive and which we call negative? What really matters physically is how they interact, their relationship. So the gauge principle says we should be free to make that labeling choice, positive, negative, completely arbitrarily. Not just overall, but at every single point in space and time independently.
Like being able to choose which way is north just for yourself right here, right now, without affecting anyone else's north.
Exactly like that. But to make that work mathematically, to allow every point that local freedom of choice without messing up the physics, you find you need something else. You need fields like the electromagnetic field to carry the information, to mediate the forces between particles and ensure everything stays consistent despite the local choices. This relational way of thinking, defining properties through required interactions, led directly to the Standard Model, unifying several forces.
And then finally, bringing it right up to date, we get to the geometry of space itself. What happens when you try and merge quantum rules with gravity? What does space look like at the tiniest scales?
You end up with something called quantum geometry. And the picture that emerges, often visualized using Roger Penrose's idea of spin networks, is pretty startling. It suggests that the smooth, continuous appearance of space that we experience is basically an illusion, a large-scale effect.
So down at the Planck scale, that incredibly tiny level of 1033 centimeters, what's really there?
It's likely discrete, not continuous. Think of space not like a smooth liquid, but like a fabric woven from individual threads. At the smallest scale, you don't see smooth fabric. You see the threads, the knots, the loops. Space, in this view, is built from these tiny relational bits. And crucially, space isn't a pre-existing background for these bits. It emerges from the network of relationships between them. Just like the properties of a cloth emerge from how the threads are woven together. No threads, no cloth, no network, no space.
Okay. So pulling all this together, what does it all mean? We've gone on quite a journey, from a cosmos seen as this rigid, eternal, absolute clock ticking down, to one described by dynamic, relational, self-organizing processes. More like an ancient city, constantly evolving, rebuilding itself.
Right, and bringing time and evolution into the very fabric of reality. It helps resolve some deep puzzles. It suggests the universe is much more about process than fixed design.
Like the old chicken and egg problem. In an evolutionary context, we know the answer. Eggs came first, laid by something that wasn't quite a chicken yet. Time allows that emergence.
Exactly. And this evolutionary relational perspective leaves us with, I think, a really provocative final thought for you to consider. If reality itself is genuinely a self-creating system, if objective reality isn't eternal or absolute, but is actually time-bound and defined by relationships, then how does that change the very nature of objective knowledge for us? For observers like us, who aren't separate from reality but are intrinsically woven into the fabric of that complex, evolving system, what does knowing mean then?